Yeah, I'm so sorry I cannot be there with you. Yesterday, the flight delay crept up to 4 hours, which would have made me like basically like die. And so I had to not come, which is terrible. But I hope I can still give you some glimpse as to what we're doing. I'll be telling you about work we did under quantum gas microscope. Where the provocative title is Cooper pairs under the microscope. If you think about it, it sounds a little bit like black milk, but we can discuss later on together. I want to use this occasion um, to remind everyone of Daniel Kleppner's memory, who unfortunately passed away recently, who gave us these wonderful quantum gases to think about in the beginning, along with, of course, a legacy on precision measurement, the physics of Rydberg atoms that we have seen before, cavity quantum electrodynamics. He was a pioneer in so many fields that now are at the frontier of atomic physics, and of course the production of Bose-Einstein condensates. And above all, he was also a caring mentor to all of us, and set um, the way we treat each other in the field. So he set an example to all of us. And he was telling the story how in these gases we should not think about particles as billiard balls, but of course as waves which at low temperatures expand and start to overlap. And that's how we tell the story in public talks and in colloquy. Here we get into this problem of quantum statistical mechanics when we have to know, are we a boson, are we fermions, what is going on. And Dan so beautifully described this in a Nova special that you should all watch, where you actually see Dan Kleppner appear several times in his office, being very confused about his identity, where to be. So this is actually wonderful to watch. And of course, now at low temperatures, all the Dan Kleppners decide to all condense in one macroscopic matter wave, whereas the fermions are sad and have to stay apart from each other. I drew this cartoon, I don't know, 15 years ago, more like as a sort of illustration. But in fact, in 2015, Emmanuel's group with Christian Gross were able to produce pictures like these, where the fermions stood like one after the other, um, uh, limited to be one side apart in optical lattice, not able to overlap. One method to get to these low temperatures is evaporative cooling, which was invented in the group of Dan Kleppner and Tom Graytek, in fact by Harold Hess. And that gave us then eventually the Bose-Einstein condensates. We celebrate 30 years, which is why it's probably appropriate to remind people it's a round birthday for these Bose-Einstein condensates. Famously, the alkali atoms took over the initial quest with hydrogen. But of course, Dan Kleppner and Tom Graytek, they didn't give up, but a few years later managed to actually condense hydrogen. Now, the detection was quite indirect. They had to look at a spectroscopic shift of their sample due to condensation. So Dan would probably have loved to see the experiment that I'm going to show you. This is on a microscope experiment built by Richard Fletcher when he was a postdoc with my group, and the work on the dynamics of rotating Bose gases that he did on the experiment were so spectacular that he's now on the faculty at MIT building his own experiment. And I'll tell you the newest experiments here, where we not only see every single vortex, if you want to, but now also every single atom in a continuum gas. We can cool bosons and fermions, so we should be in a good shape to study the situation that I mentioned in the introduction. So the idea is quite simple. You have this quantum gas in an optical trap, for example, not in a lattice. So mind you, this is a continuum experiment. So the atoms run around, but at some moment you say freeze. It's like a freeze dance, where you suddenly trap them in a deep optical lattice where they can no longer move. And then we can have all the time in the world to illuminate them if we do it cleverly, to collect their fluorescence and image them on the screen. So if you do this for the Bose gas, indeed, we see a small Bose-Einstein condensate of like 30 atoms or so, surrounded by a thermal gas of loners. You see these little dots that are all these individual atoms of sodium. That's why I color-coded it yellow. And if you do it with fermions, our case lithium-6, lithium loves red light, so that's why they're color-coded red. You see they hate each other. They don't like to be near each other. And you see by eye the Fermi hole that each fermion carves around itself. So let's go back to the situation of these waves that were all confused and starting to get their identity crisis. If you take a picture of that situation for a Bose gas, you see pictures like these, where by eye you realize this is very speckly, like the atoms are closer together than by mere chance. So they're bunching up, and that's precisely what you would expect. In fact, within one de Broglie wavelength, you expect this bunching effect of the bosons, which you here clearly see if you just extract the G2 correlation function, which tells you what's the probability of finding one boson next to the other. It is enhanced, and it does go almost up to 2, which is the theoretical value, of course, at 0 distance. And from the width of this G2 correlation function, you can also extract the temperature directly. And it's quite nice to have a direct view inside this identity crisis moment, if you want. If you do it for fermions, you see, of course, the opposite, that they don't like each other. So you see the Fermi hole carved out in a region given by their de Broglie wavelength, which at low temperatures is the Fermi wavelength, simply the interparticle spacing. And also for that, you extract the temperature from images like these directly. So that is already providing a microscopic view of correlated quantum matter, but it's not interacting quantum matter yet. So of course, that's going to be the next subject. For example, when you put two spin states of fermions into the same trap, we all know they should form a condensate of pairs at low temperatures. For strong attraction, that could be a BEC of molecules. For weak interaction, it could be a Barney-Cooper-Schrieffer state of Cooper pairs, and in between it would be a crossover superfluid that has a pair size on the order of the interparticle spacing. Now that story we talked about for maybe 20 plus years in these atomic gases, but we didn't have a microscopic view on these situations, except for famously small numbers of atoms on the order of 6, 7, 8 in Selim-Jochem's group, where they were able to tame in a deterministic way a precise number of fermions. So the idea is to throw the microscope onto images like these, where you have a vortex lattice of fermion paired superfluids. Maybe a little bit of background. This superfluid is of a strongly coupled kind, so the critical temperature is much larger than one would think from BCS theory, usually for weak interactions. In fact, the critical temperature is on the order of the Fermi temperature. It comes closest to this critical line that you see here, this dashed line, which is the critical temperature for Bose-Einstein condensation. And on this busy graph, which is called the Umura plot, which compares the critical temperature to the Fermi temperature, you see the weakly coupled superconductors on the far right, because they have a small pairing gap compared to their density due to the weak interactions. And then the high temperature superconductors are on this dashed, in this dashed region. And the newly found magic angle twisted bilayer graphene of my colleague Pablo Herrero here comes also very close to this critical line of BEC. And the cold gases hold the record for the largest critical temperature normalized by the Fermi temperature. There is also a useful connection to neutron matter. I will not claim that we can understand the intricacies of what's going on inside the neutron star, which is a terribly complicated object with pasta in there, protons in there, and complicated stuff. But like dilute neutron matter in the crust of the neutron stars is also described by very strong attractive interactions between the neutrons with a scattering length that's much larger than the interparticle spacing in terms of magnitude and therefore almost unitary. And measuring the equation of state of our gases at a million times thinner than air densities tells us something about what happens in a gas of dilute neutrons at 25 orders of magnitude higher densities. In fact, we measured a bunch of years ago the equation of state of these fermions and found in particular the ground state energy of these fermions at the unitary point when the scattering length has diverged. And it was wonderful to see a Nature paper a few years ago where they tried to obtain the equation of state for neutron matter, and they used the unitary Fermi gas as the lower bound on the equation of state. They argue that it is the lower bound, and they use precisely our value, 0.376, and don't even quote us because it's such a commonplace apparently now in the community that it's everyone knows about this. It's 0.376. We'll never forget. So that's the connection. And now enough said. Let's throw the microscope onto these interacting gases and see what we get. I kept that picture in grayscale for a reason, because we're not observing spin here. But you see by eye that, for example, in the middle picture, there are always two and two atoms paired up near each other. In the left picture, actually, these are also pairs, but they're so close together that you cannot quite see that there are two atoms next to each other. And then, as you get into the BCS regime, I cannot claim I know who is paired with whom, but I can still draw some ellipses for fun. So that's directly observing pairing and pair formation. And you can again ask, do we see this in the G2 correlation function? Yes, we do. So the orange curve is the density-density correlation function, which at short range shows this tendency to bunch up, to pair up at close range. While like fermions, the blue curve shows the G2 function for like fermions that are spin aligned. That still has the Fermi hole, of course. So from these pictures, you directly see not only fermion anti-bunching, but also that the fermions attract, from which you can extract things like the contact and the fact that they pair up. I will say more about the contact. You might not quite be tuned to this term, so it's going to be useful to talk about it. Turns out, so when a new method comes online, usually it doesn't happen in a vacuum, and so there are in fact 3 groups who have built these quantum microscopes at the time last year. By now there's more. For example, one on molecules and Simon Cornish's group on rubidium cesium. Now I did show this grayscale picture. It's of course nice to move to color TV. And so that's what we have been working on in the last half a year or so to try to get color into these images. So that means you need to image spin up and spin down separately, which is a technical challenge. I don't fully want to bore you with all the details. We can talk about it in the question session. But basically, I can tell you we managed to do it using simply a Stern-Gerlach separation of spin up and spin down, and trapping the atoms in 2 different optical traps after the separation and then imaging them. Similar techniques have been invented in Emmanuel's group for lattice trapped gases, or in our group also on the Fermi-Hubbard system. Here it's now working on the continuum gas microscope. And now, well, if you put these images together of spin up and spin down, now you see indeed spin up and spin down are the ones that are paired together. Not surprisingly at all, but still nice to see that it's blue and red that pair up with each other. So I can now, from now on, replace these cartoons that I have been showing for 20 years with actual images coming out of the lab, where you see on the BEC side that indeed the atoms like to be in very close range pairs. They're so close range that here you see them as purple, because they actually occupy the same lattice side after the image freeze. Remember, the freezing is using an optical lattice, even though the physics is playing out in the bulk. So purple means the two atoms decided to be on the same side. But then as you weaken the interaction, you see less and less of these purples and more of these neighboring pairs. And then in the BCS regime, it starts to become difficult to associate who is paired with whom, as we expect. Let me talk about the contact as one of the main parameters that describe these continuum systems. The contact, first of all, is a thermodynamic variable. It measures the change of the energy with respect to the interaction strength. In 2 dimensions, interaction strength is often measured in terms of the log of the 2D scattering length, so we shouldn't be worried about that, and a bunch of m's and h bar squares, but it's basically just the change of the energy with respect to the interaction strength. It also measures the strength of short-range correlations, quite well, naturally in hindsight, but of course, you need to realize that there is the Feynman-Hellman theorem that directly tells you that the change of energy with respect to interaction strength brings out the expectation value of 2 particles to be on top of each other at 0 distance, and therefore it is the same thing. Also, if you realize that it has to do with the probability for 2 particles to be close together, it will also determine the high momentum tails of the momentum distribution. Because if I look at short range in momentum space, I'm looking at large momenta. And so the contact is also given by the tails of the momentum distribution. And it controls further things like the strength of photoassociation signals and so on. It's a beautiful story. If you want to learn more about it, there's a very nice paper by Werner and Yvan Castin that really summarizes a lot of the things that Sheena Tan has developed before. So now what can we do? We can just read off the contact by just taking these pictures. And what we do is we just count the number of doublons in the images after the freeze. Why does that work? Well, at short range, the correlation function to have a spin up near a spin down will go like this many-body contact times a 2-body piece. That is the insight that Sheena Tan had. If you have a complicated many-body wave function, well, still, if 2 particles come close to each other, then at very short range, you're only going to see those 2 particles, and the physics must be of 2-body kind. So it's a 2-body piece times a complicated many-body thing, which is the contact. So now, if you just integrate over a certain region and you ask how many pairs do you have, that directly therefore measures the contact. So that's directly related to the doublon fraction, which we can just plot as a function of the interaction strength, and therefore directly obtain the contact as a function of interaction strength. And here you already see that mean field fails terribly in these strongly interacting Fermi gases. The mean field would be the dashed line, and in 2D accidentally gives you a contact that's just equal to what you would expect from 2-body physics, just if you had a bunch of molecules. And that's not right. Mean field forgets about the interaction in the normal state that you already have above TC. And these normal state interactions, they give you a contact that's much larger, which is this solid line. The solid line is actually from quantum Monte Carlo, and the blue dots are from the experiment, directly reading of the doublon fraction. You can actually use this these images to read off way more things. You can also read off the full equation of state if you want. The density versus the potential gives you access to the compressibility, to the pressure, chemical potential, temperature, actually, via the fluctuation dissipation theorem, and so on. I'll not go there now in this talk, but I'll just mention it, that these images just directly basically tell you everything you want to know about the thermodynamics of the system. Now, one thing I want to talk about is density fluctuations. There we can have a little reminder of what we know about density fluctuations in different states. When I learn quantum statistics, I hear about a BEC as a coherent state, and therefore I learned that I should measure Poissonian number fluctuations. So delta n squared over n for the boson should be 1. Now, if we are in the BEC regime with our fermions, the number of bosons is simply half the number of fermions, which gives me a delta n squared over n that should equal 2. Simply if I plug in the 1/2 in the right places, that's how it works out. In a zero temperature Fermi gas, however, number fluctuations are suppressed because of Pauli blocking. Yeah? I have a full Fermi C, and now I suppress my density fluctuations because I don't want to scatter out of this Fermi C. I'm completely Pauli blocked. So it should be 0. At finite temperature, of course, it's not 0. There is a sliver of roughly T over T Fermi times the number of fermions that have weakened the Fermi surface and can still fluctuate. So your delta n squared over n should be given by directly the temperature, T over T Fermi. Also interestingly, even at 0 temperature, in a BCS state, your Fermi surface is now molten and smeared out over the pairing gap. So the fluctuations should again not be 0, but actually measure now the pairing gap. Delta n squared over n is given by the pairing gap. So when you try to calculate that, you can actually use the BEC-BCS crossover mean field theory, and it's actually a homework problem in Vetter and Walecka. And you figure out actually a beautiful curve that gives you super Poissonian fluctuations. Well, if you think about the fermions as the basic building blocks, super Poissonian, in the BEC regime, but remember that's actually Poissonian fluctuations for the bosons, for the molecules. And in the BCS regime, it goes exponentially down like the pairing gap, sub-Poissonian. We can now just directly look at our gas and just measure the density fluctuations. And what we measure, it's a bit preliminary, but I still want to share it, is a curve that qualitatively goes roughly in this direction. There are 2 reasons why we don't quite measure 2 in the BEC regime. One is, well, our experiment at the time only had like 80-85% fidelity in actually correctly seeing a doublon. By now it's 95%, so we will update this curve soon. The other is physics. Even at 0 temperature, in a BEC, in a strongly interacting BEC, you don't expect everyone to form a wonderful pair. There will be quantum depletion, and that should, in fact, lower the fluctuations away from this number 2. It's a little bit of a conjecture, but and on the BCS side of things, we don't quite measure 0. Well, we are not at 0 temperature, so I'm also not surprised that we don't quite see 0 here. But so qualitatively, that goes in the right direction. But here comes a confusion. I told you this story that, BC is a coherent state, and we should measure a delta n squared over n, that's 1. But I also learned about the fluctuation dissipation theorem that delta n squared over n also should be given by the compressibility of your system times the temperature. Now that means if the compressibility is finite at 0 temperature, I should find 0 density fluctuations, even in a Bose gas, not 1. So what's going on? Well, it's useful to read the books sometimes, and it's of course all in our favorite textbook by Lev Pedersky and Sandro Stringari, where they show the structure factor for a Bose gas as a function of momentum. And indeed, overall, you think like, oh, 1 is an important number here. Yes, but actually at low momenta, which means very long range fluctuations, you start getting to 0 at 0 momentum. And the reason is sound waves come in and give you the correct amount of fluctuations that are given by the fluctuation dissipation theorem to actually make thermodynamics work out. At finite temperature, you don't quite measure 0 because now you have some thermal phonons activated already in your system. Same book, a few pages later, they show results from Monte Carlo calculations on the BEC-BCS crossover in 3D. And this curve really tries to tend to 2, as I promised, for the molecular regime. But then before it actually hits 2, it actually bends over and makes the fluctuation dissipation theorem happy again, because sound intervenes. And that's actually this in the BEC regime, the same sound mode that healed the problem before. In the whole crossover, it's called the Bogusław-Anderson mode. Usually not present when you discuss BCS theory, because for charged superconductors, you don't have sound. Sound is pushed up to the plasma frequency. But for us, of course, it's important and should come in to heal the story. So actually, we can obtain the structure factor directly from our data. We just take the Fourier transform of our images and average, and we get the full structure factor from, say, 50 to 100 shots. And observe in the BEC regime, yes, we get, well, something that approaches 2. It's not quite 2. But then as we go to stronger interactions, we start clearly to see this sort of linear downtrend here at low K, which we claim is actually sound. And sound is not present in BEC-BCS crossover theory, the simple one, because only 0 momentum Cooper pairs are included. And so the dashed line misses this completely. As you keep going to the BCS side of things, you start seeing something that looks like sound, even in BCS theory. That is basically, if you want, 0 sound of a Fermi gas that comes out of the math automatically. So this actually works out, and we didn't have to come up with some new technique to do this. We just looked at the images. We can also look at the function as a function of temperature, which is very interesting, and clearly we have to take more data to maybe bring it down some error bars. But the physics on the BEC side shows us we get actually more than the expected fluctuations for a condensate at around the critical temperature. That's expected. The Bose gas should fluctuate more. It's a chaotic, it's a thermal system. Should fluctuate more than the Poissonian Bose-Einstein condensate. And at low temperatures, it starts to come down again due to sound again. The other data on the closer to the BCS regime. We can also look at the spin structure factor directly from these images because we measure both spin states. There again, the spin structure factor, due to unfortunate definitions, it is 1/2 if everyone is paired up. It should be 1, but the definition is such that it's 1/2. What can I do? We don't quite reach that, I think, again, for possibly experimental reasons and slightly physics reasons maybe. As we go into the BCS regime, we start seeing a peak at finite momentum instead of at 0 momentum, which is expected already from mean field, which is this dashed line, which is precisely telling you that pairing is now an affair that happens near the Fermi momentum and no longer near 0 momentum. If you actually multiply this by k squared, you get directly a universal behavior governed again by the contact. So this is another way to obtain the contact if you want. And you see again in the BCS regime, the tails here are much higher than what you expect from mean field. Again, because mean field completely underestimates interactions in the normal phase. So this other way of obtaining the contact gives similar results. Now, to end, I want to quickly give you a glimpse yeah, of what we are up to. Recently, we look at spin imbalance mixtures, hunting like in the olden days for the full de Ferrel-Lakinov-Chinnikov phase. No, we haven't found it. I would have probably changed my title otherwise. But we can already start to look at correlations in the spin imbalanced gas, and we'll shorten this story somewhat. But it's interesting that in these two dimensions that we live in, the imbalance is constant. The magnetization is constant throughout the system, which is actually very good for full de Ferrel-Lakinov-Chinnikov phases, because then your wave vector, the difference in the wave vectors, which governs oscillations of the order parameter, will be constant in the system and maybe easier to find. So here is a correlation in the rather highly imbalanced regime where we think this is actually directly providing us with a picture of a Fermi polaron in these systems. I can tell you more about in the question session. Very quickly, just so that you have something to ask me about, we have also found evidence for the Fermi polaron in the attractive Hubbard gas. Attractive Hubbard model is as complicated as the repulsive one. There's an exact mapping from the repulsive to the attractive side, and this is almost to overwhelm you. Yes, there is a strange metal, but it's actually strange spin metal here for magnetization. At low temperatures, you should find a superfluid and again a full de Ferrel-Lakinov-Chinnikov state, maybe. Possibly even a more exotic D-wave antiferromagnet, which would be the equivalent of the D-wave superconducting state, putative on the repulsive side. And at high imbalance, a Fermi liquid of polarons. There I want to mention that there is actually very strong evidence that at all relevant densities, even for strong attraction in the Hubbard model, the polaron is the ground state of the system. So a ground state of the system of a single impurity of spin down atoms in a spin up Fermi sea. That's actually a little bit surprising because for strong attraction you would expect that to form a molecule. But there is not such a molecule. It's actually high in energy, and we can discuss in the question session why. I will quickly give a glimpse of the data. Actually, I think Ehsan might be in the audience, so you can also bug him about questions about the experiment, where we study this imbalanced, spin imbalanced attractive Hubbard model. And let's look at one quantity that we're familiar with from the talk, which is almost like the contact, which in the Hubbard case is going to be, again, the doublon fraction. If you look at the doublon fraction as a function of magnetization, well, it varies. Of course, it goes down at high imbalance because you have less partners to pair with. That's not so surprising. What's surprising is that the dotted lines start to agree very well at high U and in the large magnetization limit with the full-fledged theory and the experiment. Of course, the theory has less error bars. This is not yet in a regime where we completely challenge the theorists. And it gets actually a bit more clearer when we plot instead the Singlon fraction, normalized by the minority densities. You see that in the limit of large imbalance, where we should be seeing the physics of polarons, we do approach, at least if you lower the temperature a bit more, the expectation for a zero temperature polaron in this limit. So basically, I leave you with two pictures of Fermi polarons in the continuum on the left side and in the Hubbard model on the right side. And of course, this raises more questions than gives answers. So I'm happy we have some time to discuss. In the future, the goal is to throw these single atom resolution microscopes onto all these continuum systems that we are interested in. And one thing that would be actually very fitting for the conference that I didn't have time to talk about is downstairs here, the non-equilibrium dynamics of quantum Hall states of bosons, which we also managed to take a glimpse or take an image of. And there's much more to discover in these type of continuum systems with this new method. So with that, I would like to thank my group and you for your attention.
Questions?
May I ask a question? This pairing is not only about density correlation, it's also about coherent order parameters across the system. Do you think there's any hope to measure the order parameters of pairing?
That's, yeah, such a beautiful question, because honestly, when you look at these images in situ, I have no idea whether they form a condensate of pairs. Absolutely. What you can do in these systems is still use the old trick of time of flight, right? You can actually suddenly ramp to the BEC side, give time of flight, and then take a picture if you want with single atom resolution imaging, and then see a peak at zero momentum of those pairs. So that still works like in the olden days, and is great. But I think you're asking the question: can we from these images obtain the fact that they are condensed? And that's why I started to think about these number fluctuations, because again, in a coherent state, the number fluctuations should be Poissonian, and not super Poissonian. But the sound intervenes to make the story more complicated. So then the hope would be to measure it versus temperature, which we try to do, as you see in this preliminary data. I don't know whether you can still see my slides, where you should see a peak in the fluctuations, and then it should come back down as you start forming the condensate. So it's a bit more subtle to tease it out of in situ images, but I do think a temperature-dependent study of the number fluctuations could give it away. Actually, to be honest, a better way is to measure something like second sound, but I think it's a very, very intriguing question.
Lauren?
I have a question, a naive question about measuring in a spin-resolved way the molecules on the BC side. So you have two spins or two fermions, spin up, spin down. They're basically sitting on top of each other. Now, do you do this measurement of the two species simultaneously? And if you don't, doesn't the first measurement kind of affect the state? And then how do you know that the measurement of the second one is then unbiased?
Yeah, these are indeed simultaneous, and that's why it took many months between the grayscale image and this image. So it's tricky. What we do is we freeze suddenly as before, but now there could be some doublons in the very same lattice site. If we now expose the system to light, these atom pairs would immediately become molecules, fly away, die. It's the end of the story. So we need to separate them before we image. And that becomes a little tricky, but well, that's what we worked on to improve. So it turns out the lattice itself is applied in the XY direction. So in the Z direction, it's actually a whole bunch of tubes. And if we release the sheet, the light sheet in which the atoms originally live, then the atoms can fly away in this tube. And if you apply a strong gradient, they fly away into different corners of that tube. And I admit it's a little tricky because you first have to turn them from molecules into free atoms, which we do with some RF drive and magnetic field ramps. But it does work to split the molecules into two free atoms that then go to opposite corners of your tube in the Z direction. And by now we separate them by roughly 20 microns. And then we recatch them in two separate light sheets. And 20 microns is much larger than the focal depth of our microscope. So we can simultaneously now illuminate the two layers on different parts of our camera. And we simultaneously gather the photons from the two sets of atoms. So that way we preserve the information of having doublons in a given site. And that's how we see those purple sites.
I see. Thank you.
Hi, Martin. Thank you for this nice talk. Since you already stopped on this slide, so I may have a really quick trivia-ish question. Why the system size gets bigger and bigger as you go to the BCS region?
Oh, that's a super good question. It's actually physics. So in the BEC regime, the mean field interaction is small. The mean field is, sorry, mean field. What am I saying? Well, it's fine. It's actually correct. What I meant to say was chemical potential gets small because you basically suck out all the interaction energy. The bosons become rather weakly interacting, and you start to have a very small condensate. Because this is still a trapped system, right?
You still have a trap, harmonic trap.
Yes, it's still happening in this purple light sheet that I had in one of the slides. So it's a harmonically trapped system, more or less harmonically trapped system. Of course, in principle, we can also make a box in the same setup. Here we do like actually the harmonic trap because then it gives us the equation of state directly. But it's the harmonic trap that does this. In the BCS regime, you have a chemical potential that's given by the Fermi energy, so the system spreads out.
I see.
We could, of course, compensate for that. Maybe to confuse the reader less, we should probably do this, but we kept the trap the same for these three images.
Okay, then maybe kind of relevant, as I didn't realize you still have the harmonic trap. So for the metadata you show about the static structure factor measurement, and you see the kind of the reduction in SK as K goes to a smaller value. I was wondering to what extent this drop in SK can be, is due to more fundamental physics or due to the system has like finite size, has inhomogeneity across the density, things like that?
It's super good question. In fact, if you think about the trap, then sound is cut off basically by the wavelength given by the size of the system, right? So you cannot make sense of a lower k than that, a longer wavelength than that. So this is actually given roughly by the dashed line. The gray line here. The gray line is the sort of the system size cutoff, below which we cannot make sense of k, right? And it's of course an approximation to analyze this in terms of okay. Well, it's not an approximation. What we do is simply take the Fourier transform of these images, yet of course they come from a trapped system. So you might worry that it is modified. It will definitely be modified at the long range, but at shorter wavelength, you still have, of course, sound, even in the trap. And here we are looking at mostly Ks that are already quite high compared to the sound wavelength for the wavelength given by the trap size, because Kf here is 1 in these units, right? So Kf is the wavelength of the interparticle spacing. So that gives you a sense. If there's a lot of distance between the interparticle spacing and the size of your trapped gas, you're quite safe in collecting enough data in the regime where sound should exist.
Okay, thank you.
Just wondering, is there any way to measure the pairing symmetry of the superconductor? I know in this case it's probably just regular S wave, but in principle, is there a method to do it?
Super. So can we distinguish S from D wave? I think not without some clever interference, because we won't get the sign otherwise, right? And it also smells like we would like to do some time of flight. So what one would have to do is you break the pair, you break the pairs, let them fly away, and then have a look. Now, you could do this like hypothetically. On the left-hand side, you have a D-wave superfluid, which you somehow created magically. On the right-hand side, you have an S-wave superfluid. And you could use the S-wave as a beating condensate for the D-wave. It's a bit of a kind of a dream, but just thinking for 5 seconds about it, that's what you probably have to do. Break these pairs simultaneously, let them fly away, and then measure interference.
So
It's a very rough answer.
right, in this class of systems, are there proposals to do like chiral superfluids or some kind of
Oh yes,
distributed-
lots. Some people, including Emmanuel, myself, and others, are trying to look for fermionic superfluids with dipolar interactions that support p-wave pairing. You can also try to induce spin-orbit coupling on a Fermi gas to induce effective p-wave pairing also. And so there are lots of proposals how to do it. It's just difficult. Another way could be, this is very hypothetical, if you look at the fractional quantum Hall states of rotating Fermi gases and you look at the particular filling, I'm told you're supposed to find p-wave superfluids for 5/2 or I think that's further out, but yeah, there's no lack of proposals.
Thanks.
Okay, great. Well, let's thank the speakers from the morning session one more time. And now we have lunch.
Thanks for having me.